So today we're going to be spending most of our time talking about the periodic table, how we use it, what the periodic table, the numbers on the periodic table look like, and so forth. But just to introduce this, so we're going to watch a video at the end of class about Dmitry Mendeleev. But, Jonathan, a question?
Well, I have more questions about the quiz.
Okay.
Does photosynthesis occur in plants and animals?
No.
Well, I got that one wrong.
What do you mean?
I just said photosynthesis.
Right, they both. Photosynthesis and respiration both take place in plants. So that should have been both.
Wait, for this one?
Occurs in plants? Is that what you're talking about?
No.
Guys, I fixed it.
Oh, yeah. No, which organ now?
I fixed it.
Oh.
Chloroplast or mitochondria.
My table.
Oh, wait, we did this. All right. So, Dmitry Mendeleev was a 19th century scientist. He was Russian. He now there were people that had made various versions of some kind of table of the elements to organize them a certain way. But Dmitry Mendeleev did it in sort of a unique way and added some predictions that made his work sort of more significant than the others. And so Mendeleev was a scientist, and what he said is that he had worked with elements and chemicals and chemistry, and what he said is that he woke up from a dream and sort of the idea about how to organize these elements in the periodic table came to him, and he quickly wrote it down. And what he wrote down was pretty close to accurate. He said in that initial periodic table, he only had to make one correction afterwards. Hello? Yep. Okay. Thank you. Luke, you're awesome. And so he wrote down his initial periodic table, and what he did is he took the elements. At his time, there were only 56 elements that had been identified. Okay? And he put them in a table of increasing atomic mass. And so the heavier the element, he put them in order going across. Okay? Ordered them according to their atomic mass. And then what he did is the way he organized the table, the next group family down would repeat. And so what happened is he organized it so that anything that's in the same group here has some similar properties. For example, hydrogen, lithium, sodium, potassium. These elements, anything in this first group, had similar characteristics, similar properties, reacted with other elements in similar ways. Okay? And so he continued doing that. And the other thing is, you'll see over here, there's 44, there's no symbol here. This is boron, aluminum, and then we have this blank for 44, and this blank for 68, and for 72. What was unique about what Mendeleev did is he predicted that, well, we don't know anything about it yet. We haven't discovered an element, but there should be an element somewhere on Earth that would fit in here. It would have a certain atomic mass. It would have certain properties. It should be a metal and so forth. So he predicted several elements that had not been discovered. And later on, they were discovered. Scientists found these elements, identified them, and found that they agreed very closely with Mendeleev's prediction. So before anyone had discovered these elements, Mendeleev had predicted that they would be found somewhere, and he predicted their properties. So that was a pretty unique feature of his periodic table. And so he's credited with sort of being the founder of the modern periodic table.
Are there any elements that haven't been discovered yet?
Not really. All those gaps are filled in now. Sometimes, though, new elements are created in particle accelerators, and where people basically send atoms flying at each other. They smash into each other. Some stuff happens, and every once in a while they create a new element. These new elements, there's only a dozen atoms of that element, and it only exists for a very short time. But with modern instruments, scientists can analyze the results and see, oh, we created a new element here. Even though it's not a naturally occurring element, it's not anything you would ever find on Earth. So, kind of. Jonathan?
Or we just send elements flying.
And you ever hear like the Large Hadron Collider, or these huge underground tunnels that are miles long, and they can use electromagnetic forces and send these atoms flying around, and then they smash them into each other and see what happens.
That's fun.
All right, so let's talk about the periodic table, what it means, and how we use it. So the modern periodic table looks like this. Okay, yours is similar. Now there's some variation. You know, some elements are added. The older versions may not. Some elements didn't have their formal names yet, but we could use any periodic table sort of in the same way. Okay, so first off, it's developed by Mendeleev in the 1800s and lists all the elements on Earth. And again, elements, these are pure substances. Mendeleev organized his periodic table by increasing atomic mass. Our modern periodic table, however, is organized by increasing atomic number. And they go along with each other pretty closely, but there are some exceptions. So we increase in atomic number as we go across the table. You know, the first element there is hydrogen. Its atomic number is 1. Helium is 2. Lithium is 3. Okay? Beryllium is 4, and so on. And so our atomic number increases as we go across, and we go down into the next row. These rows, these horizontal rows, okay, we call them periods. In any element, we'll learn about electron shells later on in the unit, but anything in one period here has the same number of electron shells. The vertical columns of the periodic table, okay, those are called groups or families. And just as when Mendeleev organized the table, elements that are in the same group have similar characteristics, similar properties, and they interact with other elements in similar ways. Each periodic table, each element in the periodic table has a symbol, a 1 or 2 letter symbol. If it's 1 letter, it's a capital. Like hydrogen symbol is capital H. Helium symbol is a 2-letter symbol. And in that case, first letter is capitalized, the second letter is not. And you do have to be a little bit careful with that. Because if you write CO, capital C, capital O is one thing, capital C, lowercase o is something else. Capital C, capital O is what? Carbon and oxygen. Capital C, lowercase o is the element cobalt. Okay? So you have to be careful in terms of how you write the symbols. Now, some of the symbols would obviously make sense, like H for hydrogen, HE for helium. But what about silver? You know what silver is? Emma?
Isn't it AG?
AG. Well, where the heck did they come up with that?
Where did they come up
Some of you may know.
Like Jonathan?
Jonathan?
It's from Latin.
It's from Latin. Do you take Latin?
No.
No?
But
Does anybody
it's
take Latin? Okay. So many of the symbols that to us in English probably don't seem to make sense. For example, potassium is K. Gold is AU. Silver is AG. Lead is PB. So all of those symbols, they all originated in Latin. The Latin words for silver and lead and so forth. That's where those original symbols come from. Cool?
Does the atomic number measure anything?
Yes. We're going to be talking about that in the next slide. Okay? All right, so let's talk about those numbers and what they mean. Now, on your periodic table, the one I gave you, at the top in the middle, there's like a key. And it tells you sort of what all these various numbers mean. And depending, if you look up a periodic table online, the numbers may be arranged in a slightly different way. It just is a matter of style. As to, sometimes the atomic number is large and in the middle, sometimes it's small or off to the side, sometimes it's on top, sometimes atomic mass is on bottom. It just varies from table to table. But we have to know what some of these things are. So first off, atomic number. The atomic number on your periodic table that we'll generally be using, it's in the lower left corner, not all the way down, but this next to the name of the element. Okay? And the atomic number tells you the number of protons that there are in that atom. That's what atomic number is.
Can you draw that line?
Sure, if you want to. So carbon, as an example, has 6 protons. And the number of protons is very important. That's what makes an element a certain element. Any atom with 6 protons in it is carbon. And no other element has 6 protons. Okay? So that's what determines which element it is. And now overall, in general, elements on their own are electrically neutral. Their charge is 0. So if carbon has 6 protons, what do protons have? What kind of charge? Morgan? Positive. What must that mean about its number of electrons?
Must be the same.
Has to be the same to balance each other out to make a neutral atom. Yes. So the atomic number not only tells you the number of protons, but it also tells you how many electrons there are in an atom of that element. The other important number that we're going to use often is the atomic mass number. The atomic mass on your periodic table is up near the top. It's a decimal generally. Okay, 12.01 here for carbon. And the atomic mass basically is telling you how heavy an atom of that element is. It's total mass. Okay. And so for carbon, it's 12.01. And so if you remember back to the video we watched yesterday, do you remember what they said about the mass of an electron?
It was like 6 billion cars.
Well, that was the mass of a whole atom. That was the density.
Oh, I was just asking a question.
The electron has almost no mass. Okay? So really the atomic mass of an element is telling you the protons and the neutrons in that atom, the total number. Bianca, you have a question?
Yeah, if neutrons don't have any charge, what part do they play in an atom?
If you know about, so like charges, just sort of like poles in a magnet, what do they do? Like charges? No. Like charges, Courtney? Yeah, they repel. Unlike charges, positive and negative, attract. And so if a nucleus is, if it were all protons, what would happen?
The electrons would come
And the protons would want to,
and go out.
yes. The neutrons help to maintain the structure of that nucleus.
How do chemists find out this stuff?
We're going to talk about that tomorrow. Okay, about some experiments that helped us understand what the what an atom, how it's configured, how it's structured. So, atomic mass is the number of protons and neutrons. And because these things are so small, scientists have a unique unit to measure the mass of these subatomic particles. It's called the atomic mass unit. We abbreviate it AMU. And that's what the atomic mass, the units are. And in this system, a proton has a mass of 1 AMU. A neutron also has a mass of 1 AMU. And an electron has a mass of 0 AMU. Now, it's not technically true that electrons have 0 mass. They do have a tiny, tiny mass. But it's basically inconsequential. You don't need to really take that into account. It's like weighing yourself on a scale and then taking a piece of lint out of your pocket and weighing yourself again. It's not a significant difference.
So is electron like really small?
Tiny,
Smaller than
yes.
atoms?
Yep. Herschel?
Like, can you give us like an idea of how how heavy a atomic mass unit is? Or yeah.
I mean, it's almost nothing that you can conceptualize because it's so small. You know, we're talking the mass of one subatomic particle. It's just minuscule. Olivia?
What is the numbers underneath the...
This is the electron configuration. These are numbers we're going to use later on in the unit. So we'll get there. But basically, say in the first electron orbit, there's 2 electrons, and in the second, there are 4 electrons. Okay. So if the atomic mass is 12 for carbon, and it has 6 protons, how many neutrons does carbon have?
6.
Yeah, it has 6. Okay. Protons plus neutrons equals the atomic mass. All right, so let's talk about how we use these numbers. So one thing you're going to have to do, and you'll have to do this in your homework, is figure out how many protons, electrons, and neutrons various elements have. And the way we do this is pretty simple. It's not difficult at all. So when we want to know the number of protons, we just look at the atomic number. When we want to know the number of electrons, the same thing. To find the number of neutrons, we round the atomic mass, and then we subtract the atomic number. And that will tell us how many neutrons there are. So if we look at oxygen here, atomic mass 15.9994, atomic number 8. How many protons would be in an atom of oxygen? Nicholas? 8. How many electrons? Joey?
8.
Also 8. How many neutrons, Emma?
8.
Also 8. Okay, how about fluorine? How many protons are there in a fluorine atom, Nicole?
9.
9. How many electrons, Nicole? 9. How many neutrons, Courtney? No? 10. So again, we round the atomic mass, so it'd be 19, then subtract the atomic number, which is 9. So that would have 10 neutrons. How about gold? Olivia, how many protons? 79. How many electrons? Jonathan?
79.
Also 79. How many neutrons? Nicole?
118.
118. Yeah, so it has a lot of neutrons. And if you think about gold, gold is a very dense metal. And again, this will start to give you an idea about why. Because it has in the nucleus of a gold atom, there is a lot of neutrons packed in there, giving it that mass. And last, helium. Protons. Bianca.
2.
Electrons, Autumn.
2.
Eli, neutrons.
2.
Yes. All right, so we understand how to do this?
Yes.
Jonathan?
What's the number I have to worry about?
That's the electron configuration. Now, you may be wondering then, if I said protons have a mass of 1 AMU, neutrons have a mass of 1 AMU, electrons have a mass of 0 AMU, why are the atomic masses on your periodic table decimals? Protons are 1 and neutrons are 1. We should end up with all whole numbers. Zach, you know?
Electrons are exactly 0.
That is true, but actually the atomic mass doesn't really include electrons, so that's not the reason.
Like the 1 and stuff might not be accurate. Like it's accurate, but it's not like the exact number.
No, it's pretty close, actually.
Maybe they vary in size.
That's exactly why. Is because not all gold has the exact same mass. Sometimes there could be versions of an element that have a different number of neutrons. And we call those isotopes. An isotope is an atom of an element that has a different number of neutrons. So it can't have a different number of protons because then it would be a different element. So it's the same number of protons, but it may have an extra neutron or maybe missing 1 neutron, giving it a different atomic mass. So we call those isotopes. Now, an example of an isotope, carbon, let's look at. So carbon, most carbon in the universe that we know of is carbon-12. Or on Earth, I should say, is carbon-12. Okay, if you look at carbon-12, how many protons does it have? Emma?
12.
No. Autumn?
Wait. Oh, 6.
Has 6 protons. How many neutrons does carbon 12 have? Morgan? 6. Okay. Giving it an atom. This atom has an atomic mass of 12. But sometimes there is some carbon that's slightly heavier. Carbon 13. Carbon 13 has 1 extra what? Nicole? No, because then it wouldn't be carbon anymore. It has 1 extra neutron. Okay? It has an extra neutron, making it slightly heavier. There's also some carbon on Earth that's carbon 14. Carbon 14 has 8 neutrons and 6 protons. So it's even heavier. Okay? Carbon 14 is an unstable isotope, meaning that it will spontaneously decay and give off some energy. It's called radioactive. So when scientists write those atomic mass numbers on the periodic table, they're averages. So the average of the carbon that we know of is 12.01, which makes sense because carbon 12 is by far the most common version of carbon that there is, and therefore the average is pretty close to 12, but a little bit more because of the carbon 13 and 14 that we know exists.
Is there always the same amount of electrons outside?
Yes, in a neutral atom, it's the same as the number of protons. All right, let's just do these quickly. I think you guys understand well enough that we don't need to spend a lot of time here. All right, Sachin, what's the symbol for this element?
Okay.
Yes, what element is it? Zachary?
Potassium.
Potassium. What's its atomic number, Grant?
19.
19. What is its atomic mass, Kristen?
39.1.
39.1. How many protons does potassium have, Herschel?
19.
Yes. How many neutrons, Veronica?
20.
Yes, 20. Atomic mass minus atomic number. How many electrons, Chloe? 19. Is that clear, all of that?
Yeah.
All right, aluminum. Symbol? Eli.
AL.
Emma, name.
Aluminum.
Atomic number? Jonathan Cordero.
13.
Yes. Atomic mass? Olivia.
79.1.
Aluminum.
Oh, wait. 27.0.
Yep. Number of protons, Ashley.
13.
Number of neutrons, Tristan.
27. Or no. 13.
No?
26.
Atomic mass minus atomic number?
14.
Yes, 14. Number of electrons? Morgan?
13.
13. Okay, last one. Bromine. Joey, symbol?
BR.
Nicholas, name? Atomic number? Sachin?
35.
Atomic mass? Jonathan Wheeler?
Atomic mass is 79.9.
Yep, we'll round to 80 here. Protons, Autumn.
35.
Neutrons. Courtney.
45.
Electrons. Eli.
35.
Good. You guys got that?
Yeah.
That's basically what you're going to have to be doing on your homework.